Okay, well now let's move on to our next talk. In fact, our only in-person talk of the afternoon. If Ricardo could come up.
Thanks everyone, and thanks for the organization for give the opportunity to give this talk. So part of this talk I inherited from Anna Morozova that did all the collection of the data and part of the test of the neural network that I'm going to present. And I will start with this a little bit more wordy slide, but it's just for you to get it when you have the recording. So just to summarize it, the goal is to predict the total electron content of the mid-latitude, basically the Iberian, at the Iberian level of the total electron contact of the ionosphere and how it changes over time. For this, we apply 3 different methods of neural networks. Here we isolated the one because it was already studied before, implemented and published some time ago. And for that, we use, as I mentioned, these 3 types of neural networks. And we have these 3 years of data, and we also have, why we have just these 3 years and a half of data is because this was the outcome of a project that allowed us to have probes in different places in Portugal and Spain, and we have measurements for all the necessary quantities that we need to train and estimate the total electron content. So this is part of this work, as I mentioned, was done by Anna, and my knowledge of atmospheric physics ended here. And so the total electron content is important because part of our communications are coming from space, and for example, the GPS connection or the GPS signal is highly disturbed by those types of changes. And measuring it is important because as outcome of this project, we expect to have a service for private companies to get a warning if the TEC is going to change or not in the day after or in the 3 days after if you are overly optimistic. But not just the TEC itself is important, also the decomposition using PCA and basically the 2 first eigenfactors are important because, as I will show you in some slides, the seasonal variation is very important. And when you decompose your signal in the PCA modes, you get basically the trends, and the first 2 eigenfactors are independent of the seasonal variation. So you can really get the local variations of the signal and not variations caused by the seasonal effects. And I already mentioned we are trying to estimate up to 3 days, but the first day is the one that we are more confident that we can estimate, and I will explain you a little bit why in the next slides. So in the overall, why we call it PCA/neural network is not a mixture between PCA and neural network, don't confuse it. Basically, we take the measurements of the total electron content every day, we apply the PCA, and we extract the first eigenfactors and also take the mean TEC. Then we feed this to our neural networks, we train it, and then we get at the end the eigenfactors that are, we hope, correspond to what we can calculate, but estimated on the day after. And then you can also compare it and convolve later on with principal component analysis or the first 3 components, but I will not show it in this talk. So the data it was being recorded in 2014 until 2018, and we have 2 types of data, one with 1 hour resolution, one with 1 day. We apply, as I said, the PCA analysis to extract the IOFs. And then we also have associated with that, and that's why we only have this small time scale. We have all these geomagnetic indices that they were already described in the previous talks. Thanks for that. Save some time to explain it. And also some more solar-related indexes like magnesium and some other fluxes in UV. And you also have the solar flare estimation. You just have the C class, but actually in the convolutional neural network we had more than the C class. We have basically the more stronger ones. And those are the elements that we are feeding to our neural network models. So we have the very simple one, feed-forward model, that was already implemented and published by Anna some years ago. Then we developed two other ones, a convolutional neural network and recurrent long short-term memory model. So the feed-forward neural network, it was already out-of-the-box package that was implemented in R. So we take as an input for the model 31 day, or we tested with 31 and 32 days, meaning that we take chunks of the 31 or 32 days, and then we move it like a running box over time, and then we try to estimate for each one of these running box the TEC and the eigenfactors for the next day or up to the next 3 days. We took a Monte Carlo approach to try to have some estimation of error, because also some of the measurements that we are having, they have inherent error, and this is some of the details. So the neural network has some 14 layers for the mean TEC, and the IOF and IOF2. They have different numbers of layers. We have just 7 predictors on this neural network. They are described here, and for the eigenfactors. The model was converging better when we just used those elements here, those 4. The long short-term memory, those are the details, and in this case we used the same number of predictors for all the models. We tested on this one the third eigenfactor, but the results, they were not very good. Actually, they were not already very good for IO2. But you only have 4 predictors, and because the model then started to not converge very well, and those are the ones that basically 2 magnetic geomagnetic indexes, the magnesium 2 index, that is a measurement of how basically the high chromosphere is changing, and the daily mean TEC, because it's something that we are measuring. Lastly, we use the convolutional neural network. That is a rather simple convolutional neural network that is comprised of a stack of convolutional layers plus dense layers. In this case, instead of using 32, our tuning gave the best solution of 27 days. So in a way, it's good that they both models managed to be tuned with more or less the same chunks of data. That, in a way, it tells us the physical time scale of the system. So we said that, okay, between 27, ideally it should be the same, but at least they are in the same range. And we have the same 3 days of expecting. So the models that I'm going to present, the first plots, it was with this configuration. So we use 3 convolutional layers plus 2 dense layers, and we use 32 predictors. So here I tested it with all the data that I was showing before. So basically the vector magnetic field measure on the ground, plus many other solar indexes, to be expecting that even the ones who change not much could contribute for the model and give, we hope, the best results. So this is this is a little bit of a messy plot, but it tells you the variations of the daily mean of the total latent content over time. So this is the full data set. The first thing you see here is the seasonal variation. So depend if you are, because it's also related with the exposure to the sun. The UV also changes the total electron content of the atmosphere. And you see in black line that is mostly hidden, which is good, by the result of the neural network. So this is the 1 day estimation of the total electron content. And you see that most of the cases, the 3 models, they manage to predict with a fairly good accuracy the mean daily TEC. And you see already here some deviations, but in average, at least the seasonal variations are easily replicated. And these are since the other plot is rather messy, so those are the scatter plots of the distribution between what we observe and the results for the 3 different models. So you see that the 3 of them, at least to estimate the daily mean TEC, they represent rather good accuracy, although we still have some spread, at least on long, short-term memory ones. Related with the eigenfactors, the things are not working so well, at least at the moment. You still see the colors are the same axes, and you see sometimes some neural network is giving some very overshooting, let's say, data. And when you look to the scatter plots, you see that the neural network is the one that by far performed the best, but is giving, at least in this model, is giving some very nice burst value. So, but you can see already here that the other two ones, we still need to work more to make them to be valid, at least to estimate the eigenvectors. This is for the second eigenvalues. So you see this more or less the same behavior. The convolutional neural network is performing way better than the others, but still with some sort of scatter. And the other two ones, the results are by far not reliable, at least in our opinion. So you also made a task for 1 hour TEC. And here the results, as you see, are way worse, but we also have way more variation, so the neural network may be needed to be trained more. And those are the results, and the results are more or less the same compared to the ones before. So at this moment, since we also have the goal of estimating the day after, we start to think on ways that how we could improve from here. And one of the things is to try to update the neural network model every day, because we will have, not currently, because there is still a lag between the places where we have the probes and the time that the data reach to us, like an airport, for example, is not so easy to communicate with those locations. But we are aiming to have a daily updated model, because we cannot just randomly sample our data, because they are also heavily dependent on the date that we are collecting the data, because of the seasonal variations, and the day before also influence what is the TEC is going to be on the day after. But on these, let's say in Dover, I decided to split the model of the convolutional neural network in 3. So I have exactly the same architecture, but instead of before that I have the same model trained and optimized to taking the TEC value and the 2 eigenfactors. I split in 3, so I have one model that is optimized for the TEC, another model for the eigenfactors, another model for the first eigenfactor, and another model for the other. And these are the results. So here you have the gap of 27 days that I needed to have to train my neural network. And these are the results, or the best results so far, probably too good to be true, but I'm confident that they are there, of the CNN that is optimized just for the TEC values. And this is the results for the first eigenfactor. Those ones are almost on spot. I even ran a 1 epoch test to see if I was not making a mistake, and it was giving me bad results, hopefully. So this means that the model is complex enough to be able to retrieve the physical processes, although it's not assisted by any physics in the loss function. But we are also not interested actually in the physical interpretation of the model. We just want to predict the days after. In that case, the most important one is the day after. And you can see that the results are matching with a very, very high level of accuracy, 0.998. So to conclude, it was a rather short talk. So the tests are showing that the 3 methods are giving, at least for the TEC, very good results. And you may be wondering why we are testing 3 different methods to do exactly the same thing. First, it's rather tricky to have errors on those types of estimations. And we are at the beginning thinking that 3 wrong results, or if you go to the accelerating part, many wrong results. If you take the average, you get almost the correct one. So we are trying to see if you have the 3 models agreeing in a result and maybe doing the average at the end. So we are confident that you can use, although the long short-term memory, they still need some work. The CNN are by far showing the best results, although we still need to work a bit on how we make this fully automatic estimating and modeling and training the neural network every day to estimate the daily TEC, at least for the day after. The 3 days, it's a little bit more tricky because you just need a flare and all the model, as you are already thinking, is totally wrong. And at the end, and probably if you have some idea how to estimate this, we need to find a more realistic way to estimate errors on the predicted TEC value. And that's it. Thank you.
Great, thanks for a very interesting talk. Do we have any questions? Any questions from the audience? I don't see any hands. I certainly have one. Could you just clarify, when you said that you have 3 different convolutional neural networks, one for the eigenvalues, are they completely separate, or do you train them simultaneously and link them, or are they just like?
No, that I misexplained myself. So it's the same architecture that I applied before, but before I was optimizing the neural network to get the 3 values at one. Now I have exactly the same architecture, but I tune 3 times for each individual value. So it's the same architecture, train 3 times separately, and tune one for TEC, one for the first eigenfactor, and another one for the second.
Okay, and do you think that that's maybe could be indicative of there not being enough complexity in the model to do all 3 simultaneously? Because usually this sort of thing, if you have multitask learning, the machine, they get better rather than worse.
At the beginning, I thought that yes, but it could also be that so the convolutional neural networks, we need to define kernels, right? In that case, I have 3 kernels with 3 convolution layers with 3 different kernel sizes. So probably the variations that I need to have, or they are realistic in just to estimate the TEC. Actually, if you just look to the TEC, you will see that the kernel, probably the first one will be much larger because we have the seasonal variation. So we need a larger kernel just to tune it that we don't need on the other 2. So the tuning, let's say, just taking the eigenfactors, we are removing this larger kernel that I needed for the seasonal variation.
Okay, that's clear. I think we do have a question.
Good talk. What's the resolution of the prediction made by the
It's one day.
network? 1 day?
Yes, we are getting in order less than 10% in 1 day when you take into the future, like unseen data. And the 3 days, it's
the best.
you cannot predict if a flight is going to happen after 2 days. So
Okay.
if there's like under quiet sun conditions, let's say, it performs better. If there are some activity or strong activity on the sun, it's totally off. So it's something that at some point you need to put in the code that if something happened in that day, just say it's not reliable.
Okay. All right. Thank you.
Great. Any other questions from the room? Do we have any online? Oh, Kama has one. Offline.
Yeah. So can you comment a little bit more on how perfect your models are doing, especially the CNN?
So they are doing pretty well, as we could see on the plots. And this allows us to be confident at some point that they are complex enough to retrieve it. It can be a total overfitting of the data, which is a bit difficult to estimate because we cannot just randomly do a validation set because the actual date, it's important. So I cannot just say my last 20 days I will not train on that and compare it to with this like we do usually. We have validation split. On this we cannot do it because actually we always need the previous information to do that. So it makes us somehow assuming that we will be able to get data in a daily basis and update the model. Actually, we did in a very smooth test with synthetic data. That we can do this every day. We think the model is realistic, reproducing what we expect. Although it's still the issue with, as I said, if there is a strong event on the sun prior to our measurements, like in a very, very short period of time, we will not be able to rely on the results. That's true. Because if there's a flare happen and I collect the data now and flare is happening 10 minutes before, I'm telling, oh, this is going to be the TEC tomorrow, and yeah, I'm already gone.
Great. Well, if there's no other questions, let's thank Ricardo again.